Is that correct? Okay, so you guys are good students. You never have to worry about it. Okay, glad to hear that. So let's talk about, come back to this two-level system with a quantized photon. Okay, and last time we know that when we quantize the light, we get the electrical field as a direction, by the way, in a cavity. Okay. A vacuum electrical field, and then a creation and annihilation operator. And this is like the mode distribution along the z direction. Okay, this is what we get last time. And then we know this operator, when you act on n photon, it gives you n minus 1 photon. Okay, act on plus give you n plus 1 photon. And then also we know the Hamiltonian for photon, that's the En field, okay, is a half. Okay, and then so this particular question, okay, put a single atom in a cavity, okay, in a microcavity, is called JC model. Okay. Janus-Cummings model. Okay. Okay. This is the simplest case in light and matter interaction in a full quantum regime. Okay, and today we're going to briefly solve it. Okay, it's never a full solution. The full solution takes a long time, and want to briefly solve it, and then show you the critical difference between a classical, the classical light and the quantum light, what you can expect. Okay. And there's a hypothesis. Well, there's an assumption we need to make. First is, where do we put the atom, right? The E field has a Z dependent. So we put the atom, well, because we want the maximum interaction between an atom and the light. So we put at the position sine kz is either 1 or minus 1, right? So you have the maximum intensity. Okay, so we erase this. We choose 1, okay, for simplicity. And we go back to whenever we try to solve a quantum problem, we have to write down the Hamiltonian. Okay, so the Hamiltonian here would be the Hamiltonian of light plus the Hamiltonian of atom. Okay, or somebody even write interaction, but we already include interaction in the atom last time. So previously we know what's the atom. Okay, we have ground state E1, and then we have this matrix element. Okay, E2. This is excited state. Okay, so if you're in 1, you get your energy is E1. If you're in state 2, your energy is E2. And then also we have minus Q x E. Okay, this is the potential energy of an electron or of a charge inside the E field, and this X is like three-dimensional. Okay, describe the displacement of the electron. Okay. And then last time what we did is that, okay, to this we know the identity matrices. Right, we know this. Okay, we plug this in. We get and let's see, minus mu 1, 2. Right, so up to this point, it's the same as like a few weeks ago when we talked about light and matter interaction. And now the next step is kind of straightforward, right? We have the E. We just plug in. Okay, this is the E field in quantum mechanics case. We just use this here. So let's write it down. This is the first row, okay, minus mu 1, 2. Ex. Okay, vacuum. The field of vacuum. And then this is the important part. Okay, we have 1, 2. First go with A, and then 1, 2 with A dagger. Okay, just write it down. And then here also 2 EX epsilon 0, and then 2, 1 A plus 1, 2. Okay. So at this point, well, first of all, this is, well, later you will see this is relatively easy to calculate. But one thing you notice is that this term, all these terms actually has a physical meaning. Okay, think about it. A is annihilation operator. It means the system loses 1 photon. Okay. 2 to 1. This 2, 1 means if you act, if the system is on state 2, then this 2, the inner product is 1, give you state 1. Okay. This operator is that it's able to flip your state from 2 to 1. Okay. So what this operator means is that if you are in state 2, upper state, and then you have n photons, okay, when you hit with this, okay, what happens is 2, 2 is 1, and then you get, well, A, okay, and then A hit on this. So what happened is think of it, they act independently. Okay, this act on the atom, this act on the photon. And what you will get is you go to ground state, and then your photon number reduce 1. Okay. That doesn't make any physical sense, right? What it tells you is that your atom move from upper state to lower state, and then you lose 1 photon. The real physical process should be you're from upper state to lower state, and then you emit a photon, right? That's the energy conservation law. Okay, so the first term here, violate energy conservation. Okay. It's identical to the rotation wave approximation we say in the classical case, but here it's more straightforward. You just apply this to a state, and then you see whether the energy is conserved during this process. Okay. And this violate energy conservation, and so should this one, right? This one, what it can do is it can, let's see, 2, 1, A. When they act on 1, N, one hit with this, and then give you state 2. A dagger hit with N give you N plus 1. Right? So what it means is that ground state N photon. After this operation, somehow you move your atom to upper level, and then you emit a photon. Okay? It's the reverse of what should happen. Okay? Violate energy conservation. Okay, so these two. So you see, actually, yes.
So we're throwing these terms out in just a hand-waving logical way.
Right.
Is that just because our math isn't perfect and so these terms appear when they shouldn't? Or why is it that we have those terms and then we have to reason and say they shouldn't be there?
Yeah, that's actually a...
Is it because we're still improving the theory?
No, it's because of the time scale. Okay, so there's only a limited time scale that you can violate this thing. Okay, so if you really write it down, this one, the time scale of it happening is 2 omega t. Okay. If you're looking at this, if you're looking at your system at the time scale of 1 over 2 omega, then you can partially see this. Okay, and the reason is there's a certainty principle here. Okay, so you can kind of do it. So it exists, but just at the time scale that is so fast and none of us can observe. Okay. Yeah. So, but it's a very good question. Okay. Okay. So now we have our Hamiltonian of the atom. Okay. E1, 1, E2, 2. Okay. Let's be a little bit aggressive. Okay. Add in the light. Okay. This is the Hamiltonian of the light. And then this part is the Hamiltonian of the interaction. And then we can write it as okay. So here we have defined h bar g equals minus mu 1, 2 ex. Okay, this is just to simplify the equation. Okay, this is also called coupling strength. Okay, it has a unit, the dimension of frequency. Okay, and so when you look at this, still no idea what to do, right? So what usually happens is that you think about the process. The process is, this is a single atom. What you can do is either absorb a photon or emit a photon. So the logical way to do, the logical thing to do here is to consider your system. There's only two possible states. One is that your atom is on, we should really have a better notation. So let's do this. The ground state related, okay, we'll write it down as spin down. It's like lower energy. Okay? And upper state is upper state. Okay, lower and upper. So we can think about the system. So now suppose we start from upper level state with n photon. Okay, the only alternative state that doesn't violate energy conservation is lower state with n plus 1 photon. Right? Okay, you can emit 1 photon and then you come down to lower state, but you can't emit 2 photons when you come down to lower energy state. So this can form a set. If you start from here, then the only state you have to worry about is this one. Okay, but then, you might ask, what if I want to inject a random number of photons, or what if I inject a state where the photon number is not the eigenstate? Okay, that's possible. You have to calculate it separately. But here we limit ourselves to n and n plus 1 photon state. Okay. So what's the benefit of this? Okay. Previously, we have shown that if you only have 2 states, then you can write everything as a matrix, right? One state can be like 0, 1. The other is 1, 0 as a vector, right? And then you use matrix calculation. You don't have to carry all these things here. So, okay. So this is the argument. There's 2 states we concerned here. Okay. And then the next one we want to simplify is we want to throw away this half. Okay, half of energy here. The reason is the system this energy doesn't participate. It's just a number in your Hamiltonian. Whenever you Hamiltonian hit with, like say, a wave function, it just produces a number. Okay, there's no operation you add to that state. And equivalently, what this means is that you can shift your energy level. Okay, because only the relative energy between 1 and 2 matters. The absolute energy shouldn't matter, shouldn't change the physics here, how you interact. So one is that we can throw away this, okay, or you can keep it if you're not sure about it. The second one is we want to make the system look a little bit symmetric. You can, previously we have E1, E2. Okay, they're both positive. Now what you can do is you can move the energy 0 in the middle. Okay, and then E1 become minus H. Okay, half of the energy difference between them, and this is plus half the energy difference between them. And then we also have so this just create a symmetry in your Hamiltonian. And then when you calculate it, actually, you'll start to see the benefit. Okay, so here we further go to Hamiltonian equals to minus H, okay, 1. Everybody is fine with shifting the 0 point of the energy, right? Okay. So this is, in general, this is okay as long as you're in non-relativity case. Okay, when you're in relativity case, you can't do this because whenever you shift energy, you add mass to a system. E equals mc squared. Okay, so we're in non-relativity regime. We're fine. Okay, plus okay, and then plus. Okay, and then plus So starting from here, there are two paths you can take to do the calculation. The first one is, since you know all these operators, you know the outcome when they apply to this two state, right? So you can assume a wave function, and it's a linear combination between these two states. Or you can simply write it as AT. I keep making this. And this looks almost identical to our previous, to our classical case, where you define a wave function and then you use Schrodinger equation to solve it. Okay, and then this path is kind of a duplicate to what we have already done in the classical case, and so I would probably leave this as a final exam. Okay, so take a note. Okay, and this would while there will be 20 points in the final exam that's quantum related. I want to differentiate the score a little bit. Okay, so this could be one, very high probability. And then if you do calculate this, what you will find is that even n equals 0, okay, when it's in upper state and there's no photon, you're still able to solve a Rabi oscillation. You'll still be able to see that your state is doing like up and down, down to up, down to up, up to down. Okay, you're still able to see that. That's called vacuum Rabi oscillation. It's a very famous phenomenon, and somehow also show that it's kind of proof to Schrodinger's uncertainty principle, because it shows that the E field is not zero even you have zero photon. And so today we want to take a different approach. The approach is kind of used a lot more in experiment, especially for experimental group, is solve the eigenstate of this system. Okay. The reason is because of that Rabi, oscillation. What happens is that if you put n photon and then the atom at the upper state, the system will start to oscillate. It's not a steady state. Okay, what the steady state means is that the probability of seeing this state does not change with time. That's a steady state. And steady state is the easiest thing to observe in experiment. So other than solving the Schrodinger equation like this, you can also solve the eigenstate, and that will be able to tell you a little bit of information. Okay. So for the eigenstate method, what we would do is that we don't even need to write down this. Okay. This is the eigenstate equation. Okay. If you plug in this state back into the Schrodinger equation, what you will see is that there's a phase okay. This will be the solution to the Schrodinger equation, and then you will see your amplitude is not changing with time, only a very fast oscillation phase. So So the way you solve eigenstate is also the way you solve the steady state. Okay. So now let's look at it. And then here, we can actually start calculation using this. But there's some notations like papers want to use. Okay, they typically don't write down as this. So even now, if you pick up a paper, well, although they write down the same Hamiltonian, you will have difficulty understanding them. So we kind of, in this class, I think we should at least do this a little bit. Okay, and so let's first look at this. Okay, this part. If you write it down as a matrix, what will happen is it will look like -1, 0, 0, 1. Right? Okay, 1, 1, 2, 2 corresponds to the matrix. 1, 1 element, 2, 2 element. And this matrix is defined as a Pauli matrix Z. Okay. So whenever you see this, you know it's this. So for us, it's actually we just use the matrix. It doesn't, like for this class, it doesn't even matter if we have this or not. Okay, we just need the matrix. But in a lot of literature, they don't write it down as this. They write down as sigma z. Okay. So this is the first thing, and then okay, this one is the simplest form. Okay, you cannot do anything more. Now let's look at this too. Okay. 1, 2. What you can do, as we said before, is that to lower the 2 state into 1. Right? It's to lower the ground state, well, upper state, move the upper state to lower state. So we define it as this operator. We define it as sigma minus. Sometimes people write it as sigma minus. Okay, either way. And in the matrix, this is 1, 2, right? Okay. This is equivalent to the annihilation operator in photon. So it's simply lower the state by 1, and then similarly we'll have 2, 1. Okay, this will be defined as plus. Okay, plus 0, 0, 1, 0. So it's to move your state from lower state to upper state. And when you write it down in this way, somehow, while the physical, well, somehow it looks more straightforward in what it means in physics. Okay, so first is it's this. It's the original. It's the Hamiltonian of your atom. Okay, lower state, upper state, and then it's the Hamiltonian of your photon. Okay, and then you get h bar g. You have lower your state from upper to lower. This will create a photon, right? And then, okay. I still don't understand why people put it on top. Let's put it. Yeah, it looks so much like the Hermite conjugate. Okay. Plus. Okay. So create a photon. Atom move from upper state to lower state. Correspond to emission. Absorb a photon. Atom move from lower state to upper state. Correspond to absorption. Okay, so this is a quantum way you write them down. And now so this is actually also called the Hamiltonian, or JC Hamiltonian. Okay, whenever you look at papers like this is probably the first equation they will show you. Okay, and it's good to know what this weird operator means. Okay. And the next part we're going to write them down as matrix, because these are just definition. Well, you can use definition to do calculations. Okay, so here then here is a little bit tricky. Okay, so let's say H is a 2x2 matrix. Okay, this is, let's see, C11, well, H11, H12, H21, H22. Okay, so what the matrix need to do is to, actually it's just a representative of your Hamiltonian. Okay, so what you really need is H times lower state m plus 1. Okay, it's the same as, let's say, matrix Hm times 1, 0. Okay, does that make sense? If your H act on lower state with m plus 1 photon, and then you can definitely know this will this will map to a coefficient. Let's see, C1, C2, right? So if you calculate it, it must go like this. It's a linear combination between these two eigenstates. So what your Hm will do, well, if you write it down as a matrix, you want to make sure that this goes to C1, 0, 1 plus C2. Okay. So in an algebra sense, linear algebra sense, these two will be equilibrium. These two will be equal to each other. Okay. And matrix, then you can do a lot of things. You can calculate the it's more straightforward to calculate, let's say, eigenvalue and eigenstate in a matrix expression. Okay. So let's look at this first. Hm, if we multiply 1, 0, okay, what you get is H11, H21, right? So now you calculate this. When H act on this, you just do them one by one, okay? Just do them one by one. First of all, it's a lower state, so you get the energy of lower state. Okay. And then you have n plus 1 photon. So this term gives you n plus 1, also this lower state. Okay. And then this term is 0, right? Because you're in lower state, and the upper state inner product with the lower state is 0. Okay, this term is 0. This term, you have lower state operate with the lower state, you get into upper state. So first on H bar G, you get into upper state. And then this is annihilation operator. Annihilation operator reduce a photon by 1, and then create a coefficient in the front, right? So this is n, and because we act on n plus 1, so here's n plus 1. Okay, so by this you know H11 is this plus this. Okay. Okay. And then H21 equals to this. Okay. Does it make sense? Simply mapping, just to map this algebra onto the matrix. And then make sure that when you are in the matrix format, the outcome is the same as if you just calculate these states. Okay. It might look a little bit strange, but when you do enough quantum mechanics problem, you kind of naturally write it down. Okay, this is very handy way to handle the two-level system. And then similarly, we can get, so I'm not going to repeat it, but H22, you just act on 0, 1. Okay, and then what you will get is H12 and then H22. Okay, so H22 would be plus okay, H12 would be the same. Okay, so in this way, we can write down our Hamiltonian in a matrix. Let's just double check. Well, it looks a little bit tedious at first, but you know, once you're really good at this, you can actually jump from here to the matrix form. Okay. So so to save some space, we first define delta omega. You see, because on resonance, you will see small omega equals to capital omega, right? That's on resonance condition. Your cavity resonance frequency is the same as your atom transition frequency. Okay? So that's usually the absorption and emission happens. Right? So what we define this parameter would be extremely useful. We define as the difference between them. Okay. We define as the difference between them. And then when you use this, plug this in, you can see, okay, will equal to omega minus delta omega. right? So there's a minus 1/2 here. So you get n plus half h bar omega. Okay. And then plus 2h delta omega. And then here you have h bar g n plus 1, the same h bar g n plus 1. And then here you have n plus half. You see this, instead of E1, E2, you now see a very symmetric form. Okay. Okay. So this is your Hamiltonian. So the eigenstate of a Hamiltonian, or eigenvalue of a Hamiltonian, when you write it down in matrix form, would be extremely easy. Okay. What you do is you take okay. Okay, I is 1001. Okay. You can kind of derive it, simply use this. Okay. You can see this one equivalent to this. So we now have an equation we can solve to get the eigenenergy of our system. Okay. And then and this times this minus this times this is 0. That gives you the eigenenergy. Okay, and then, well, we can repeat the math here, but let's just give you the answer. Okay, when you multiply these two together, there's a e squared. Okay, so there will be two solutions. One is, well, okay, plus minus okay, so this is your eigenstate, and this is called this is the Rabi oscillation in quantum case. Okay, so let's look at this eigenstate. It's actually quite interesting because let's think about it. Okay, in the simple case, delta omega is 0. Okay, the photon energy and your atom transition energy equals to each other. Then these two possible states, one is you're in lower state with n plus 1 photon. And what is its energy? The energy is n+1 photon plus the lower state energy, that's -12, right? And then what's the upper state energy? Okay, its energy is n photon, and then plus upper state energy. These two are the same, right? Energy conservation, right? These two must be the same. But what this equation tells us is that these two states are not eigenstate. Okay, the energy of these two states is not the same as the energy of the eigenstate, so they're not eigenstate. And this is understandable, right? Because we already explained if you put n+1 photon in the cavity and then put the atom here, what will happen is that it will start to do Rabi oscillation. You will flip to the top and come back and then do this oscillation. So of course, they're not eigenstate. Eigenstate means you stay there forever. Okay, you don't change. So what really happened is that the atom and the photon are coupled. Okay, are coupled to each other by this. I don't know if any of you know the hybrid mode in waveguide, two waveguide coupled together, and then you create a, well, it could be either microwave or optics. Two waveguide, when you move them together, you create coupling between them, and then you will have more like plus plus, and then plus minus. Same thing. It's like whenever you have coupling, you create a hybrid mode. What this mode is, part of it is photon, and part of it is atom. Okay, it's hard to imagine, but you can, well, one thing you can do is that you can actually solve the eigenstate of this, and then you will see it's a hybrid between these two. Okay, and then the plus minus sign would be if the delta omega is 0, you will actually have plus minus minus plus. Probably minus plus. Okay, so this would be actually be the eigenstate. So it's a hybrid state between these two, between the upper level and the lower level. So your atom, if you think about it, your atom now, it's neither upper state or lower state. It's in the middle. Your photon is neither n photon, n+1 photon. It's also in between. Okay, it has a probability of being upper state, or lower state and upper state. Also probability of being n photon and n+1 photon. Okay, it's the same thing as any other coupling, and probably you encounter in your research or not. So you will see the similar effect. Now, the second thing I want to mention here is G. Well, first of all, G is not 0. Even you have 0 photon, right? G, we defined it. I erase it. Okay, so G, I think we defined it as minus h bar G minus mu 1 2 times Ex times the field of the vacuum, right? So this G is not even 0, no matter how many photons you have. Okay, so the coupling is there. It's a coupling provided by the vacuum field. And so this is interesting. So even we put this to 0, we put 0 photon, this term is still not 0. Okay, this term is still not 0. So what will happen is, okay, if you plot delta omega here, and then you assume n equals 0 photon. So two energy state, originally they should look like this. Okay, if G is 0, you plug it back. There's plus minus, and then when delta omega is 0, they cross. Okay. But when G is not 0, there's kind of like a band formed here. There's a forbidden area where the energy doesn't, well, where the eigenstate never comes to here. Okay, and this is called vacuum Rabi splitting. Okay, also it's called anti-crossing of your energy level. And let's see what this would tell us in experiment. Okay. First of all, let's assume there's no atom. No atom. In experiment, what you will see, this is a resonator, right? And then you input a photon at the frequency. Okay, you input n photon. Let's see. What you see, this is well, because this is a cavity, right? So what will happen is you detect the transmission here. And then when it's resonance, when it's resonance with the cavity, your light can couple in and then couple out. So you have transmission, right? Just like a regular Fabry-Pérot cavity. And then because you have a limited photon lifetime inside the cavity, there's some leakage, okay? So there's some bandwidth. It's not a delta function. Okay, there's some bandwidth. It's just the same. Well, it's the same as like let's say LRC oscillator. Okay, it's the same. Any type of oscillator, you input some energy into it, and then it will give you a response like this. Okay. Now let's see when we have atom. One atom. Oh, okay. Thank you. When you have one atom, and then you input one photon. Okay, one atom at lower state in the cavity. Okay, and then you input one photon. So for this, we know that there's n equals 0 because n plus 1 is a lower state photon number, right? So if this photon couple inside, there will be one photon when the atom is at lower energy state. Okay. So what happened in this case is that because your eigenstate, eigenenergy, is no longer photon energy plus atom energy. Okay, it's no longer this. Its energy is this. So when you try to excite the cavity, the only way to do it is to have your energy match the eigenstate energy. Okay, that's the way you put your state into an eigenstate, and then it gives you a constant transmission. If you're not in eigenstate, your transmission will have time oscillation. Okay. So what will happen here is the two energy states here are separated by this h bar. Okay. And then in the n equals 0 case, this 2 came out. Okay. So omega r is 2g, n equals 0. Okay. So now what will happen is, originally, if your input omega, if your laser frequency, well, if your photon frequency is the same as omega, the cavity frequency, you have output. You're able to couple inside. But now, because there's energy difference in your eigenstate, so your transmission will look like this. Okay, and here is Hg. Okay. This is because the coupling of the atom and the cavity shift the eigenenergy, so that to excite an eigenstate or to enter the eigenstate, you need to shift the energy of your photon. Okay, and of course you can see it now. If n becomes 1, you input 2 photons. Okay, if you input 2 photons, then this becomes 2 times, okay, this is 2g, n equals 1. Okay. So your state becomes okay, the splitting increase. And what can you do with this? This is actually a photon number discriminator, right? It's kind of tell you how many photons you have. Okay, if you input at this frequency with 1 photon, then you get transmission. Okay, so if you fix your photon frequency to here, then the output is always 1 photon. If you have 2 photons, then while you will see the 2 photon transmission, it actually get reflected. It doesn't go through. Okay. If you have higher photon number, also it's reflected. So this is kind of a device you can make to guarantee that you can generate a single photon. Okay. And what's even better is that, well, we can actually extend this plot. You can have 3, you can have 4. Okay. You can kind of select the photon pair. Okay. At this frequency, only 2 photon states can transmit. Okay. At that frequency, only 3 photon states can transmit. Okay. So it's like, I think people either call it photon. Well, if you put your frequency here, people call it photon anti-bunching. It's like if you input a lot of photon, only 1 pass. Okay. If you put it here, it's called 2 photon bunching. So only 2 photon state can pass. All the others reflected. Okay. And then continue. Okay. So this is kind of the very straightforward quantum device you can make by making a 2-level system into a cavity. And so from here, well, you might wonder why we're not using it, right? So I can walk you through how difficult it is. Okay. first of all, you want, well, first of all, there's a line width here, right? Okay. And then the G is basically mu12 times the vacuum field intensity. This is extremely small. Think about it as one photon, and then it's smaller than that. Okay, so this number is, really extremely small. And then I think last time we explained this is look like this, something like this. So to make this vacuum field larger, what you have to do is you have to shrink your cavity to really, really small. Okay. So part of the reason that in the midterm exam that the output of the photon is very low is because we just focus it in a 1 millimeter square space. Okay. The fact is you can do it with 1 micrometer square, and that gives you an increase of like 10 to the 6 efficiency. Here is the same thing. You have to squeeze it really, really small. Okay, this is the first thing you do to increase the G, so that you have a larger splitting. Okay, the second thing you have to do is you have to decrease your line width. Right, you have to make your cavity like almost perfect, so that the photon can stay inside for a long time. And otherwise, let's think if this is very wide, let's see this very wide, and then wider than the splitting, then you see you can't really make this device very useful. So you have to have your cavity with very long lifetime. And the third one is you have to prepare your atom. Okay, you have to prepare your atom into, let's say, ground state, which is relatively easy, and then you have to deliver the atom into the very small cavity. Okay, so there's a delivery system you need to make, and usually if the atom is good, you kind of have to do it in low temperature, so you have to put everything in a low temperature chamber. And finally, there's usually your atom and cavity will have a mismatch in their frequency. Okay, so there's a way you have to do to actively tune your cavity frequency. And normally that was done by temperature tuning, but since you want to cool down your system, sometimes that might not be an option. So people add like piezo control here to move the mirror a little bit. Okay, so I want to show you a real device, what it looks like. And the single atom, single cavity was actually pursued by just a few groups. That's how difficult it is, just a few groups in the world. And one of them is Jeff Kimball in Caltech. He also happened to be the first people to do the squeezing of light, okay, when he was in Texas A&M. And then, a lot of us actually really thought he should win the Nobel Prize, but unfortunately when this field is called cavity QED, cavity quantum electrodynamics. But when the Nobel Prize was awarded in 2012, it's on camera, so I shouldn't say that. Okay, so anyway, so we respect their decision, but Jeff is a great guy. I think he really should make the list. So this is the experiment. See this Rabi splitting. Okay, when you scan it, you really can see in the middle there's no transmission. And why there's one higher, one lower? Because your cavity frequency is not on resonance with your atom frequency. Okay, so if your atom frequency is a little bit towards this side will have a higher transmission. Okay, and it's extremely difficult to control. And this is their experiment, I think in 2004. And this is the setup. Let's turn off the light. Amazing, right? So there's a chamber to host. Well, first of all, the cavity itself is usually, the smallest is about 10 micrometer size, okay? And then you need to trap your atom or drop your atom. First, you have to cool it into almost zero temperature, and then you drop that atom near your cavity, okay? And then ideally, you will have a trap to stabilize your atom inside the cavity, okay? And then you need a single photon source, okay, to probe your system, right? You don't want to use a classical light. So this is what it looks like, okay? And then, most of this experiment is extremely difficult to do. Like most of the, Caltech PhD in his group, they get probably one publication per 5 years. Okay, you have to spend really dedicated about 5 years to finish one job, and then, but of course, usually that paper will be a Nature paper or a Science paper. Okay, and but of course, when you apply for job, there's limited universities or national lab that will be interested in your work, because when the chairs see this, they see money. You need a lot of money to make it work, and a lot of time to make it work. So, but anyway, this is still a very active area. And then now that I think part of the area is going into. So one of Jeff's approach is that he wants to eliminate the trap for the atom. Okay, he wants to use vacuum field itself to trap the atom. Okay, a remarkable idea, and I think they have a theory paper out in 2014. I don't know if they're able to make the device or not. Okay, so the other trend is to do it in use something called MV center. It's an artificial atom. Okay, it's not a real atom. It's a defect, and that defect somehow shows two energy level system. And then you can find that defect in a lot of semiconductors materials. So what people try to do is now you don't have to trap that anymore because it's in your material. It's a solid state. And then you find that defect, and then you build a cavity around that. Okay? And then the cavity you use something called photonic crystal. Okay? It's a remarkable idea proposed by a professor in Berkeley in 1987. So first you find the MV center. It's like an atom. And then what you can do, this is a top view. Okay? It's actually very small, much smaller than this. Then what you can do is how you build a cavity? You drill holes around it. And you guys are familiar with band gap in semiconductor. If you have periodic potential well, you create a band gap. What the band gap can do is that there's no electron at that frequency, at that energy and that momentum. There's simply no electron state, so electron cannot, propagate. So this is the same idea, but in photon, you build periodic photon structure, so that the photon cannot propagate. Okay, but only a defect in the center, so the photon can be localized here, but not anywhere else. So you can actually build a cavity in this way. And this type of cavity, their size can be as small as one wavelength. Okay, so it's really remarkable. So you really reduce the V. I think the V is lambda to third. Okay, you really reduce your V a lot. And then, for example, if you think about it, if you reduce from 10 micron to 1 micron, there's a cubic law here, so you get 1,000 boost, okay, in your V. So this is really, and I think theoretically proposed in 1987, and then around 2000, there's a lot of work, active work, I think both in Caltech, Harvard, MIT, also a lot of other labs, and then still going very strong in this field. It's called photonic crystal. Okay, and that's it for today. Okay, and if you have any question about your score, email me, and then we can go over it. Yes.
Will you post the solution to the midterm?
I try not to because I want to recycle the.
Sure.
And so what I recommend for question 15 is that you carry the dimension in your calculation, and if it shows up the dimension is watt, then you're fine. Okay, the number doesn't matter because you can't really see. Well, if you miss a 2, how can you supposed to know, right? There's no way to check. Okay, yeah.
What about in the diagonal directions? The photons
Oh yeah.
travel diagonally?
So that one you make your structure really thin. It's almost like a single mode waveguide, and then there's some total internal reflections. Okay. Yeah. But it's not that well confined because any defect on your surface will kind of scatter the light out. Okay.
Right, but I'm saying, so not in the third dimension coming out of the board, but going, so you have a periodic.
Yeah, on both directions. Yeah.
Lattice, right?
Yeah, yeah.
But what about diagonally?
You mean this direction?
Right.
Yeah, so this is a design you need to do. Okay, you can actually build a design that